So the first homework that is on section 5.1 that was covered last week is due this Thursday, September 1st. Submitted by uploading to Canvas. I expect that I should have some time at the end of class today. Questions that I have. Definitely done. I tend to leave time for to handle questions on homework at the end of class, just because I have an expectation of covering a certain something each day, and if I spend too much time on questions or going down a rabbit hole or something, then that knocks us behind. So we'll see how it goes. Okay. I'm going to take a look at the schedule we have here. Assignments. Okay, so homework. So today's subject is part 2. That's going to be homework 2, and that's due September 8th and so on. Okay, so the main idea behind Gram-Schmidt Orthogonalization is we've seen how when you are expressing a function in a Hilbert space in terms of an orthonormal basis, or even just an orthogonal basis, then it's very easy, relatively easy to compute the coefficients of your function f of x in that basis, because you can compute each coefficient independently of all the other ones. Problem is, you need an orthonormal basis, and sometimes those can be hard to come by. And I'll give an example of a very straightforward basis that is not orthogonal to normal monomials. If you'd like to express a function as a extension polynomials, in other words, power series. So it's a linear combination of 1x, x squared, x cubed, and so on, or even a shifted polynomial basis, x minus a, or so it's 1, and x minus a squared, x minus a cubed. Those functions are not going to be orthogonal with respect to any ordinary inner product. So it would be nice if you have a basis that is not orthogonal, that you convert it to an orthogonal one, or orthonormal one. And we have a process that will give us that, and that's called the Gram-Schmidt Orthogonalization. So the idea is, we have a set of functions that, while not orthogonal, is at least linearly independent. And generally, collections of functions like polynomials of different degree will all be linearly independent. And let's suppose that they span a given vector space. And certainly they're going to span some subspace if they're linearly independent. And I'll refer to these functions, the non-orthogonal ones, as chi1, chi2, etc. I think I'll just using the notation from the textbook for that, just for consistency. And we want to obtain from chi1, chi2, and so on, or for a normal set of functions, phi1, phi2. So I'll show how the process starts, and then you'll see the pattern, and I can give you the general Gram-Schmidt algorithm. So the first thing you do is, because we want an orthonormal set, so we have to be orthogonal to each other, and they have to be normalized. In other words, have a norm of 1. So you take your first function from your non-orthogonal set. I just realized I was pronouncing these chi1, chi2. I guess that would be chi1, chi2. Yeah, that's what's supposed to be. All right, so whatever. So to get phi1 from chi1, just normalize it. Don't have to worry about it being orthogonal or anything. Right now, we're only considering this one function. So any function that is normalized is a one-function orthonormal set. So, this is all it takes to get the ball rolling. And keep in mind the norm that we're using, the one is induced by a scalar product. So you take the scalar product of chi1 with itself and take the square root. Now, we're going to use chi2 to get phi2, and in such a way that phi1 and phi2 are both normalized, but also orthogonal to one another. Now, we're going to consider the two properties independently, or in sequence. First, we're going to ensure orthogonality. Then we're going to take care of normalizing, because normalizing is the straightforward part. Orthogonalizing, orthogonal takes a little more work. So what we're going to do is we're going to find an intermediate function, psi2, and we want to choose psi2 in such a way that it is orthogonal to phi1. In other words, their scalar product has to be 0. Once we have psi2, then we get phi2 by normalizing it. So then phi1 and phi2 will form a 2-function orthonormal set. And we're going to prescribe a form for phi2. So phi2 is equal to chi2, our second non-orthogonal function, plus a multiple of phi1. So we're going to find the right constant, which I'm calling C12 here, to ensure that this scalar product turns out to be 0. I got you thinking, like, well, how can you be sure that there is any constant that's going to work? And you're going to find out because you're going to be able to obtain it. What you do is I take this equation that defines psi2, and I take the scalar product of both sides of it with phi1. So the left side is the scalar product of phi1 of psi2, which I'm requiring to be 0. So we're going to have 0 on the left side. On the right side, I take a scalar product of this whole thing with phi1, but keep in mind the linearity of scalar product. So scalar product of this sum of two terms breaks down into the sum of two scalar products. And then this scalar, C12, that can be pulled out. Now I have this equation that I want to solve for C12. So here we take into account the basis we're trying to get are 5 functions. They're all orthonormal. That means the scalar product of any one of these 5 functions with itself has to be 1. So on this right side here, this becomes 1. And now I have, it's trivial to solve for C12. I get this. So this is the magic scalar that I need so that psi2 is orthogonal to phi1. So here, where I summarize the process I've just described, how do I get phi2? I use psi2 first by subtracting off the proper multiple of phi1 from chi2, and then I normalize the result. So now phi2 is orthogonal to phi1. Phi1 and phi2 are both normalized. So phi1 and phi2 are a 2-function orthonormal set. Questions about how that was done? Now, continue the process, get phi3. So phi3 has to be orthogonal to both phi1 and phi2. and we have to normalize it. We're going to go through a similar process. We're going to prescribe a form for phi 3, and then take a scalar product of it. Phi 2. So here's my form. So I take chi 3 as a start. Then I have a multiple of phi 1 and a multiple of phi 2. So notice I need an additional term. That's because I'm trying to make it orthogonal to two functions rather than one. So the idea, similar to how I got phi 2, I'm going to require that the scalar product of side 3 with phi 1 and phi 2 both are 0. So since I have two conditions to satisfy, that's why I need these two unknown constants. One of them will not be enough. Once I find the right value for C1 free, C2 free, I can normalize the result, and then I have a free function or orthonormal set. So just as before, I had my form for side 2, and I took the scalar product of phi 1. I need to take the scalar product of this form with both phi 1 and phi 2 separately. So I take this scalar product of phi 1, require it to be 0. This is the scalar product of the right side of a form of side 3 with phi 1. And that gives me one equation. And I take a scalar product of this equation again with phi 2, require that to be 0 as well. And I get these terms here based on the form of side 3. Here I use the fact that phi 1 and phi 2 form an orthonormal set. This scalar product is 1. This one is 0. This one is 0. And this one is 1. So, the first equation is going to allow me to solve for C1 free. Second equation gives me an expression for C2 free, and here are those expressions here. Notice my indexing scheme. C1 free is minus scalar product of phi 1 with chi 3. Here we have C2 free minus a scalar product of phi 2 chi 3. So Cij through this whole process will be minus scalar product of phi I with chi j. So it'll always work out that way. So here's the overall process for phi 3. You start with chi 3, subtract off the correct multiples of phi 1 and phi 2, which are these scalar products of each phi function with the function you're orthogonalizing against, which is chi 3. And then you normalize the result. So now phi 1, phi 2, phi 3, they're all orthogonal to one another. They're all normalized. They make an orthonormal set. there's a pattern we see here. To get phi 1, all we did was normalize. Phi 2, we subtracted off one term, then normalize. Phi 3, we subtract off two terms, then normalize. And that's what that pattern is going to continue. So by extrapolating from that, this is the general Gram-Schmidt process. So each psi j is chi j minus these scalar products times the previous phi's. Look at the index. K goes from 0 up to j minus 1. I'm trying to get phi j. Like I mentioned, all previous phi's. That's what we're doing. We're taking each new function chi j from our non-orthogonal set, and we're orthogonalizing it against all previous phi's. That's what subtracting off these terms does. And then we normalize that, and we can add it to our orthonormal set. And that's the whole Gram-Schmidt process. So we, however many chi functions we have, we generate that many phi functions. So a set of chi functions that's non-orthogonal is the basis of some vector space. Now we have an orthonormal basis for that same vector space. I'm going to illustrate the Gram-Schmidt process with any questions about this derivation. All right. So here's an example. A scalar product would be integral of the scalar product f and g is the integral of f conjugate. Remember, star means complex conjugate. It's using a textbook convention. F conjugate times g integrate and from -1 to 1. So we want polynomials that are orthonormal on the interval -1 to 1. So our non-orthogonal set that will orthogonalize using Gram-Schmidt is a set of monomials that I mentioned earlier, 1x, x squared, x cubed, and so on. At least since we're dealing with polynomials, the integrals are relatively easy to evaluate. So my functions chi j will be equal to x to the j. Now, in my derivation, I numbered the chi functions, chi 1, chi 2, chi 3. For convenience, I'm going to number from 0 in this case because we have x to the 0, x to the first, and so on. So we're going to take chi 0, chi 1, chi 2, and orthogonalize them by Gram-Schmidt to get phi 1, 0, phi, to get phi 0, phi 1, phi 2, and so on. So here the Gram-Schmidt process begins. So psi 0 is just chi 0, which is 1. And then to get phi 0, we normalize psi 0. We have to divide it by the scalar product of a function 1 with itself and take the square root of that. So we write out what that is. That's going to be integral of 1 squared from -1 to 1, and then we take the square root. Well, the integral of a constant over some interval AB is just different. It's b minus a, it's the difference of the endpoints times the constant. So the integral is 2. So we got to take the square root. So we get 1 over square root of 2. So this is the first member of our set of orthonormal polynomials. 1 over the square root of 2. So that's the constant function. So when you're taking polynomials, your non-orthogonal set, it should be all polynomials of different increasing degrees, degree 0, 1, 2, and so forth. When you orthogonalize them by Gram-Schmidt, you will again get a set of polynomials of degree 0, 1, 2, and so on. So constant function is 1 over square root of 2. Now we need the second function. So now we take chi1, which is x, and we subtract off this. This is what the Gram-Schmidt algorithm prescribes. We take the inner product of, or scalar product of phi 0 chi1. So q minus 1 over square root of 2 is phi 0, and then chi1 is x. So this is our scalar product we need to compute. And that is multiplied by phi 0, which is 1 over square root of 2. Now, for convenience, I'm going to pull out the 1 over square root of 2. So I can multiply by this 1 over square root of 2, and I get 1/2, just to give it the pesky square roots. And now my scalar product will be the integral from -1 to 1 of 1 times s ds. And I'm using a different letter here because I have x out here. So I don't want to, so it wouldn't be good to use x here. Now the integral of a polynomial of odd degree over symmetric interval, like -1 to 1, that's going to be 0. It's an odd function. So that works out nicely. That psi 1 is just x. And now I normalize it. So I need to divide psi 1 by its norm, which is the square root of the scalar product of psi 1 with itself. So now I'm going to work out this integral, which turns out to be 2/3. But then we take a square root of that, and we're dividing by that. So to finish off the algebra, it's square root of 3 over 2 times x. So that is phi 1. So right now my set of orthonormal polynomials has 1 over square root of 2, and then square root of 3 over 2 times x. Any questions at this point? Now we continue. From chi2, we're going to get psi 2. We subtract off the appropriate multiple of phi 1 and of phi 2. These are the multiples that we subtract off. Do by these scalar products. So it's chi2 scalar product with your previous phi. It's phi 0 here, phi 1 here. So here I fill in what everything is, what all these functions are. We have all these square roots, so I just go ahead and multiply those together, just to make things a little cleaner. And then we have integral of s squared ds for this one, and then here we have x and x squared, so that gives me the integral of s cubed. Again, we use the fact that we have a polynomial of odd degree on symmetric intervals, so that integral is 0. And then here, even function on a symmetric interval, it's you integrate from 0 to 1 and double the result, which turns out to be 2/3. So this is what we end up with: x squared minus 1/3. And that is orthogonal to phi1 and phi2. Then we normalize. Take x squared minus 1/3 is divided by square root of the scalar product it with itself. That's going to get a bit ugly. I'm not working through all the details here, but this is the integral that needs to be evaluated. Once you evaluate it, you get 2/5. But then you take a square root of that, and you're dividing by that, so you get the square root of 5/2 up top. Oh. Wait. No. Not true. It's scratch that. I forgot about the factor of 3/2 here. So that's included in this integral also. This that's a word. Cheating and evaluating this integral out loud. Okay. The actual value, just have a marking video. The actual value of this integral is 8/45. So you take the square root of that, divide by it, and then this is what you get normalized. So now we have phi0, phi1, phi2, 3 orthonormal polynomials that cover the space of all polynomials that be up to 2. And then you could continue this process, continuing Gram-Schmidt by taking like x cubed and orthogonalizing it against phi0, phi1, and phi2, and so on. Like this would be the next polynomial if I were to actually work out the whole thing. Questions about this process? I should mention that these polynomials that I've been showing you are closely related to what are called the Legendre polynomials, which we'll learn a whole lot more about later. Legendre polynomials are orthogonal with respect to the scalar product that I've been using, the integral of f conjugate times g on -1 to 1. So when you have a set of orthogonal polynomials, you want to know like, what interval are they orthogonal on, and what is a wave function. In this case, there is no wave function, or you can say it's just 1. Now, the Legendre polynomials, like I said, they are orthogonal. They're not orthonormal. You have to multiply by these scaling factors, which turn out to be square root of 2 plus 1 over 2, to make them orthonormal. The nice thing is, if you, like I said, these are orthogonal on -1 to 1. Suppose you wanted polynomials that were orthogonal without a wave function on a different interval. You wouldn't have to go through the Gram-Schmidt process all over again. You could take Legendre polynomials and perform a change of variables. So mapping from the interval -1 to 1, where they're orthogonal, to your interval, where you want to be orthogonal. That leads to, for example, what are called the shifted Legendre polynomials. Those are orthogonal on the interval 0 to 1. Now, as you saw, Gram-Schmidt is pretty cumbersome. Also, it takes, to generate each new polynomial, if you're taking monomials, 1, x squared, and so on, and applying Gram-Schmidt to those, you see that to generate each new polynomial takes more work than the preceding ones. That's just because of Gram-Schmidt, it's subtracting off more terms each time. But it turns out it's possible to generate orthogonal polynomials in a simpler way, more efficient way than that. That's what I'm going to show you now. And I'm going to describe it in basically using an induction-like process. That if we assume that you've generated a set of polynomials of degree up to n minus 1 that are already orthonormal, and you want to generate the next one, if you do it using Gram-Schmidt, you're going to subtract off n minus 1 terms. N terms. But now I'll show how you can get around that. So we're assuming some scalar product over some interval, some wave function, so it's very general. We're going to assume that each phi function for an orthonormal set has a degree that's equal to its index, like we have been doing. So normally what you do, if you follow what I did in the previous example, if you want polynomial degree n that's part of this orthonormal set, you would take x to the n and orthogonalize by Gram-Schmidt. But it turns out to be easier if you instead orthogonalize this function, you take your previous orthonormal polynomial that's of degree n minus 1, multiply that by x to make it degree n. Because you could take any polynomial of degree n and orthogonalize against it. Doesn't matter which one. And get the orthonormal polynomial you need. So now we'll carry out Gram-Schmidt with this instead of x to the n. Let's see what happens. So just writing out what Gram-Schmidt would be, that's what we have here. So polynomial you're orthogonalizing, and then you're subtracting off these terms, where you're taking scalar product of that function, x phi n minus 1, times each previous phi, that scalar product times that phi, so subtracting off the multiples of phi j, and then you normalize the results. So at this point, it's not apparent how we're saving any effort. That's what I'll show you now. We're going to take a closer look at this scalar product that we have to compute for each of these terms. Phi j with x phi n minus 1. Just want to make sure I don't know if I put this in here. Yeah, I need to be rigorous, I'm going to need to include this. We're going to assume that they are real value. I don't want to mess with complex numbers. That's going to throw things off. Or at least complicate matters. Okay. So here's our scalar product we need to compute. So the functional orthogonalizing x phi n minus 1 with phi j. But now I'm going to write out what that is in terms of our definition of our scalar product. Oh, wait, that'll be that. That's the integral. Okay, so now we're going to have, since everything here is real, I'm not going to conjugate anything. So phi j, and then of x, and then phi j minus 1. Wait, sorry, it's n minus 1. X dx. Okay. All I'm using is the fact that multiplication is associative. Because the way I've written the scalar product, I have x associated with phi n minus 1. But I don't have to do that. I can associate it with phi j. So I'm going to put parentheses around this. So now I can move the x over to the other side of the scalar product, the other operator. Now, how does this help? I use the fact that phi n minus 1 is, we already know it's orthogonal to all of the 5 polynomials of lesser degree. But that also means it's orthogonal to any linear combination of those lower degree polynomials. So phi n minus 1 is orthogonal to any polynomial of lesser degree. Now, phi j is of degree j. So you multiply by x, it's of degree j plus 1. So this scalar product is going to be 0 if this part, x phi j, is of lesser degree than this part, phi n minus 1. So if j plus 1 is less than n minus 1, or in other words, if j is less than n minus 2, this scalar product up here is 0. So for j, starting from 0 all the way up to n minus 3, all of those are 0. In other words, all the terms in this summation go away, except for the last 2. So now your Gram-Schmidt looks like this. So we have a polynomial we're orthogonalizing against, and these are the only 2 terms from that same summation, so I haven't changed them. They're the only ones that are actually non-zero. So go ahead and compute those, and then we get psi that's orthogonal to the previous phi, then we normalize it to make it orthonormal. In other words, each new orthogonal polynomial depends only on the previous 2. That's called a 3-term recurrence relation. So the new polynomial, the 2 that it depends on, the 3 terms total. So that's the nice thing about orthogonal polynomials, is that they can be generated a lot more efficiently than an orthonormal set can normally be generated using Gram-Schmidt. It's called also referred to as a short recurrence relation. It's not one that keeps growing as you move through your set. So questions about how this worked out so nicely? It's all a matter of keeping track of degrees. You're taking a scalar product of 2 polynomials. What degree are they? If one of them is a member of an orthogonal set, it's orthogonal to all polynomials of lesser degree. And that can be, turns out to be used to prove a lot of things. One interesting fact about orthogonal polynomials, I don't think we make use of it in this class, it's definitely useful elsewhere, is, as you know, a polynomial degree n has n roots. Those roots might repeat, they could be complex, even if the polynomial is real. But when you have polynomials that are part of a orthogonal orthonormal set, it can actually be proven that such a polynomial degree n has n roots that are real, they are distinct, and they fall within the interval AB that's used to define the scalar product that is used to establish orthogonality. So Lagrange polynomials, for instance, they're orthogonal on -1 to 1. So it's known that their roots are real, distinct, and lie within -1 to 1. That's actually very useful for approximating integrals. For more on that, take Math 460. So I mentioned one family of orthogonal polynomials, Legendre, and also shifted Legendre. Here are several families of orthogonal polynomials. And what you can see over here in the right column are which intervals they're orthogonal on, and if there's a weight function involved. So for instance, Legendre polynomials, there's no weight function, or there's an applied weight function of 1. Whereas the Chebyshev polynomials have a weight function of 1 minus x squared to the -1/2, also in the interval -1 to 1, which goes to infinity at the endpoints of that interval, but is well defined inside the interval, so that's good enough. It turns out that out of all these sets of polynomials listed here, only one of them is actually orthonormal. That's a Laguerre polynomials here. We have this Kronecker delta, which I believe I showed you in a previous class. Delta mn is equal to 1 if m equals n, 0 otherwise. So the Legendre polynomials are not orthonormal because if you take the scalar product of Pn with itself, you're going to get 2 over 2n plus 1, you're not going to get 1. But what that means is, using these formulas, you see how you can normalize them, rescale them so that they are orthogonal. I should mention the notation here. Here the star does not mean conjugate. Like here we use Pn to refer to regular Legendre polynomials. Pn star is to refer to the shifted Legendre polynomials that's distinguished from Pn. So that's unfortunate choice of notation, like the textbook. Same here we have a Chebyshev polynomial of the first kind, Pn, and then the second kind, Pn star. So some of these polynomials we will see later on in this class. Now each scalar product you can conceive of, whatever interval, whatever weight function, gives rise to a different set of orthogonal polynomials. Now, I've shown you Gram-Schmidt for orthogonalizing functions, but really you can deploy Gram-Schmidt to orthogonalize vectors in any kind of vector space. It doesn't have to be a function space, it can be vectors in Rn. And the same process applies. In fact, they teach us in linear algebra course. I think here we teach it in our second linear algebra course, which is Math 426, 526. But I'll show you how you do that right now. So here we have 3 vectors in R3, so A1, A2, A3, that are not orthogonal. They're not normalized. So you use the same Gram-Schmidt process. You're just using the appropriate scalar product. In this case, for a scalar product, we're just going to use an ordinary dot product. And the whole process is still the same, because all you need is a scalar product, which also induces a norm for some normalizing. I get the first vector, my orthogonal set. So A1, A2, A3 will be orthogonalized, give me B1, B2, B3 that are orthonormal. All I have to do is normalize A1, so that's the square root, but divide by the square root of the dot product with itself. So a dot product of this vector with itself would be 1 times 1, plus 1 times 1, plus minus 2 times minus 2. So a dot product of this vector with itself would be 6. So I'm taking this vector and dividing by the square root of 6, and now this vector is normalized. Now for the second vector, here at B2 prime, ultimately I want B2. B2 prime is playing the role of psi, previous description of Gram-Schmidt functions. So I take my second non-orthogonal vector A2, and I subtract off this scalar product times my first orthonormal vector B1. So then I fill in what everything is. Here's my second non-orthogonal vector. This is the scalar product, a dot product of B1 and A2. And then this right here is B1 reproduced. Then I work it off the algebra, vector operations. And this is my vector that is orthogonal to B1, but it still has to be normalized. So I divide it by the dot product of it with itself. Something seems strange here. Sorry. All of these vectors. Yeah, they are orthogonal to each other. They are all normalized, so they are correct. I think I'm having a situation where I'm second guessing myself. Oh, okay, I see what I did. Okay. All right. So here we have 1 over square root of 2, which would be square root of 2, times this vector. But that would be the same as, but that simplifies to this. Like, how come we don't have a square root 2 here? It's because I took the denominators of 2 and I pulled them out. I have to trust my notes more. Okay, so that's our second vector. And then the third vector, we have our third non-orthogonal vector. Subtract off these multiples of our previous orthonormal vectors, B1 and B2, described by Gram-Schmidt. So I have these dot products to compute, so B1 of A3, B2 of A3. And then work it off of vector operations. And this is our vector that is orthogonal to B1 and B2, which is not normalized. So then I do the same thing, divide by dot product with it itself, simplify as much as I can, and this is what I get. I should mention, like, this vector right here that needs to normalize. Since you're going to normalize it anyway, you could just ignore the 2/3. You can just take this vector 1, 1, 1 and normalize it. It would be the same thing because the 2/3 is going to get canceled by something anyway. So just as a convenience. So here we have these vectors that span the same space, R3, as the original non-orthogonal vectors, and end up being orthonormal. So it's same process. So Gram-Schmidt works on whatever function space that has a scalar product, and you just use that scalar product consistently, and the norm that's deduced by it is a square root of the scalar product itself. Any questions about this example? Also using the bracket notation. Vectors. Okay. Yep, that is the end of the notes anyway. But we have some time, so let's go. Anyone want to start with homework? Okay.
I have a question on 10.
Okay. See, I think what I need to do is I want to have a problem in front of everybody, so I'm gonna unshare and reshare. I'm not supposed to share my whole screen. Trouble with that before. Oh, I can share my whole screen. I might want to put some things in the notes. Okay. 5.1 number 10. Okay.
I just didn't know how to use the direct notation. Like, I don't really understand the question though. I get far from good.
Oh, okay. All right. All right. Okay, let me ask you this. Well, direct notation is really only about how vectors are labeled and how scalar products are written. I mean, scalar products are written the same way, regardless of where you have the angle brackets and then F vertical bar G, no matter what. It's bring the bracket together. What you could do is the direct notation is actually not an essential part of this problem. So what you could do, and I'm actually not concerned about how you write it, is if you were to write F as an expansion in terms of these functions of phi n, and then also equal to the different expansion in terms of these functions of chi n, and set them equal to each other, then you can try manipulating that equation to get a formula for the unknown coefficients. And keep in mind what you can do with equations. Like, for example, how do we go about getting a formula for the coefficients of an orthonormal expansion in the first place? How do you make, because you got these two summations equal to each other. Use a different letter for each. And how do you make terms go away to isolate the coefficient you're after? Because that's what you're trying to get. Like, you're going to have known coefficients on one side, unknown coefficients on the other side, which are what you want to isolate.
Can we use the summation where it gives you the identity for it?
You could have, I don't think you would need it. Yeah. So this is more about what you can do with orthogonality and scalar products and things like that. Not a long thing. Other homework question? I mean, it is a whole 2 days before it's allegedly due.
Yeah, discrete mathematics is over you because it's Wednesday, not Thursday, that's due. It's not.
Okay.
Don't look at it.
Oh, yeah. Gotta keep these chronological. I'm sure also warrants this stuff being turned in on time. Okay, last chance. At least before I stop the recording. Of course, I imagine there'll be some time on Thursday as well. I'll try to leave time for that. I guess we're done.
Sorry.
Well, just under the wire.
For number 12, like, how did they get rid of the scalar product for like E in the function space of A, B, like in the second line?
Okay, so
So like A and B have the variable E, like in the line above.
oh, here, okay. Oh, because what happens is, okay, when you take scalar product of A and B, so the scalar product needs to follow the distributive laws. So you would end up applying the distributive property to scalar product of this and this, which means any the constants A1, A2, B1, B2, you pull them out, and you'd be left with scalar products of E1 and E2. But those are the standard basis vectors, like the IJ from, so those scalar products, E1 and E2, E1 hat, E2 hat are orthogonal. So those scalar products are either 1 or 0. I just realized, wait a minute. Oh. Sorry. I goofed. I guess we're not supposed to assume that E1 and E2 are just I and J, because that would give you the standard scalar product. So, so really what's supposed to happen is, and you still have to follow the distributive property, but then the scalar products of E1 hat and E2 hat would have to be equal to the coefficients of these terms. Okay. Whoops. I screw up once each class today. It's the time I caught it before we all left. No, it's my other class. I realized a mistake shortly after everyone left, and I actually did go back to the class and record a video segment on that. So yes, I'm that obsessive. But when it comes to teaching anyway. So. Okay. That's the fear that all teachers have. If they make one mistake and their students' lives are ruined. That's their fault. Yeah. Okay, so now that I've exposed my neuroses to everybody. Okay. All right. Really calling it good now before anything else goes wrong? Okay.